Okay, in the second video in this series for week 2, I want to talk about our event-related designs, and this is what stands typically in contrast with the block design. So you've already watched the first video. You know that I'm fond of block designs. I think that they're a very sensible thing to use under normal circumstances, but there are lots of questions that you just can't answer with the block design, and we talked about a few of them in the previous video. In an event-related design, instead of having events that sort of summate, what you're going to do is you're going to have events that are individual and separate from one another. So for instance, in this particular plot, you can see that there are a series of single punctate events, things that happen in time, boom, and then it evokes a hemodynamic response function. And if you then wait until that hemodynamic response returns to baseline, you can then put another event in and get another response. So that's the basic idea of an event-related design, and it's absolutely fine. It works perfectly well, but there are a couple things to think about. One is that it takes a lot of repetitions of those events to collect enough data to make enough of a signal that you could detect it. I would say, as a rule of thumb, anything less than about 25 successful events in a condition is probably going to be on the very small side in an event-related design. The other thing is these make for really long and boring experiments. Like if you have a trial and then you have to wait 21 seconds until the next thing happens, participants really struggle to do that because it's difficult to sustain your attention when there's so little going on. So it's a challenging paradigm in that form, and it does lead to these very long, boring experiments. The other problem is that each one of those events is evoking a very, very small hemodynamic response. That is to say, the signal isn't very large. And if you recall from the first video in this series, it was really small when I showed a single second event. So for instance, in this plot, I'm showing events that are happening about 20 seconds apart, so waiting till the hemodynamic response function finishes, versus block tasks. And what you can see is that the evoked response is much larger in the block. In fact, it's about 5 times larger, right? And what that means is that it's 5 times easier to detect. If the effect sizes are larger, they're easier to successfully detect, which would mean that you would need a very much longer run of data in order to get comparable effects in terms of sensitivity if you were just using a pure event-related design. So in other words, the statistical efficiency, your ability to detect actual changes in a purely event-related design with like a long interstimulus interval is terrible. I mean, it's really grim. So you might think, well that's because you're waiting 20 seconds, for each event. What if you were actually sort of move them a little bit closer together so that you had more events in the same amount of time? The problem with this is it actually makes the problem worse. Right, so these are examples where you're using a fixed intertrial interval of 16 seconds, 8 seconds, and 4 seconds. And what you can see is the height of the evoked response actually gets smaller and smaller, because what's happened is you get the peak, but you haven't allowed it time to get back down to the trough. You've had another peak immediately after it, which means that the difference between the peak to the trough gets smaller and smaller as you put the events closer and closer to one another. So this is just to sort of illustrate it. If you had a blocked design and that represents the optimal sensitivity, so 100% sensitivity, a purely event-related design that had events that are happening every 20 seconds is just under a fifth of that, right? So 18%. And by the time you get down to events that are happening about every 4 seconds, it's about a 20th as sensitive. So you want to bear that in mind when you're thinking about event-related designs. The good news is you can improve on that. The problem there was the fact that there was a fixed interval. So that is, there was always the same length of time between the peak and when it started to come back up again. If you add some random, what's known as temporal jitter into that, so there's variability from when one event happens to another, then you get variability in how these events summate. And this image is just an example of that. What you can see is on average I have these 1-second events that are an average of seconds apart. But of course some of them are close together and some of them are further apart. When they're close together, you get this sort of summation. You get higher signal in the HRF. And then of course longer apart means that you have time for it to go back to baseline. So you get bigger differences between the peak and the trough. And when you get a whole set of events that summate together, then you get this larger evoked hemodynamic response, so larger signal that you're measuring. And that gives you greater sensitivity. So there's a really classic paper by Anders Dale in 1999 where he analyzed this sort of from a purely theoretical level and was able to show this plot, which I'm just going to take a second to explain. So in this plot, there are two different types of event-related designs happening. In one, there's a fixed interstimulus interval. That is, events are happening at a fixed interval in between. Those are the ones shown with X's and the dotted lines. And you can see it's this line here. Okay, so what we're showing on the y-axis is efficiency, and what we're showing on the x-axis is how far apart these events are in time. And what you can see is that by the time you get to about 20 seconds apart, that's when it becomes optimal, because you've allowed the hemodynamic response function to return to baseline, and you get a full peak activity followed by a return to baseline. However, even so, that's not very much signal. As I pointed out, it's about a fifth of what you would get in a block design. So, and it only gets worse as you put the events closer and closer together. In contrast, the other line, which is shown with what I'm going to call pluses, and it's not a dotted line, it's a solid line, suggests that if you have random sampling of your events, that is to say there's a random distribution about how often they happen and when they happen, there's this temporal jitter, then as you put them together up to about the point where they're about 2 seconds apart on average, you get benefits, really dramatic benefits in sensitivity, and you can see that here. In this case, if you put them together closer than 2 seconds, you start to violate one of the assumptions in the analysis that relates to sort of linear summation. So in fact, you get a dramatic drop-off in sensitivity. So you don't want to go below 2 second average. However, if all you have is random events relative to rest, then if you have them an average of 2 seconds apart and they happen in random timings, that's going to be the optimum sensitivity for an event-related design. It is still considerably less than the efficiency that you would be able to get with a block design, but it's much, much better than anything where you have a fixed interval between events. So this is important not just in thinking about trials, but sometimes if your trials are complicated and have subcomponents, then there are different types of events within a trial. So for instance, this is a delayed match to sample experiment, right? It's a working memory experiment. Somebody sees a picture of an apple, then they have to wait 4 seconds, and then they see an array of images, and they have to say, well, which of these images did you see originally? And they had to keep in mind that they saw an apple, and therefore they chose the apples. Okay. So it's a basic kind of working memory experiment, but normally the parts of the experiment are divided up. There's an encoding phase, that is when you see that apple, you are encoding that memory, putting it in your mental storage, then you're holding it in working memory during the delay, and then you're retrieving it from your storage and then making some kind of decision during that final choice phase. And you very much may want to separate those as individual events. But it's tricky, right? You can't in this particular case because all of these timings are fixed. So that is to say there's a 2 second window during encoding that's always immediately followed in those 2 seconds by the delay phase, the working memory phase. And that's always exactly 4 seconds. And then there's always this 4 second decision phase. So there's no temporal jitter there whatsoever. And as a result, any analysis that you do can't tell those things apart. There's no sensitivity to those differences. So what you can do, for instance, is add temporal jitter during your delay. So for instance, if you change this delay to something random between 4 to 8 seconds, now all of a sudden there's a difference between the encoding and the decision phases, because you don't know for sure that it's always going to return to this, the hemodynamic will always return 4 seconds, sometimes it'll return 6 seconds, sometimes it'll be 7.3, sometimes it'll be whatever. And that jitter is really critical for identifying the two different event types within a trial. So my point here is just simply that this timing, temporal jitter aspect is absolutely essential in any event-related design. And it doesn't matter whether it's timing between trials, which is essential, or timing within trials, different events within a trial, which is also essential. If in this kind of an experiment, you would need both, right? So for instance, not only is this delay jittered, but the intertrial interval here, the interstimulus interval, is also jittered. So temporal jitter is an absolutely essential part of any event-related design. Now, I've talked about the scenario where you have something happening versus something not happening, right? Just rest. But a lot of times we're interested in more complicated comparisons. So that is to say we have a couple of conditions and we're interested in the difference between A and B. So maybe you're interested in whether people recognize faces and houses differently. So you're showing them pictures of faces and pictures of houses. And maybe there's also rest conditions. But what's really interesting is houses versus faces, right? And in that scenario, you're not comparing houses versus rest or faces versus rest. You're comparing these two conditions directly. And in that scenario, it's not a 2-second average temporal jitter that's important, but something in the sort of 4 to 8 second range. As soon as you have more than a condition in rest, such that you have 2 or more conditions that you want to compare with one another, you need to have slightly longer blocks between them in order to maintain sensitivity. And for that, you need trials that are separated by 4 to 8 seconds. Or, as I just mentioned, events within a trial, like in that working memory task, they also need to be separated by 4 to 8 seconds. Now, having said this, random is a tricky thing to do, right? So the key is it needs to happen before you start testing your subjects. This is part of the way you design your experiment and implement it. These random trials, random timings of the trials or the intervals between events in a trial need to be part of the program from the get-go. If they aren't, you did everything fixed, and then you collected the data, there is no way to modify the data to improve it, right? You've basically collected crap data, and you need to just throw it all out and run the experiment again and do it correctly. So one of the things that people are interested in is thinking, well, random means that it could be okay, but it could be bad, right? I mean, that's the catch with random. What if I randomly selected things that happened at fixed intervals? It could happen. How do I avoid that? And there are tools for doing this. So there are tools for doing what are called like Monte Carlo simulations. So what it'll do is that you give it certain parameters and it'll create 10,000 versions of your experiment, and then you run each of those timing versions of the experiment through an analysis of the efficiency, and then you just pick the one that's most efficient, for instance. And that's all well and good, but the theoretical most efficient is going to be a block design. So it could randomly take your experiment and turn it into essentially a block design if what's key is that you're getting large blocks of the same trials near one another, and then rests, and then large blocks of the same trials of a different condition next to them as well. So you do have to look at these things carefully and just make sure that it's there's probably a strong reason why you chose an event-related design and not a block design. And if that's the case, you don't want your algorithm to sort of take your event-related design and turn it into a block design. That would be bad. So there are tools for this. There's one called OpSeq, which is Optimized Sequence by Doug Greaves' group. There's a genetic algorithm that Torwager and Tom Nichols put together. And there are various others. In general, I don't find them super useful, so I don't normally bother with these kind of things. When I have, what I find is that it does exactly what I said. The most efficient ones are the things that it's turned into many little block designs. And that's not what I want out of my event-related design. Okay, so what are the advantages to an event-related design? Well, the first and most important one is that it detects these transient events, right? That is to say that you can do things that are happening rapidly. So the go, no-go paradigm, those no-go trials are transient by definition, and that's what you want. That's good event-related design. It does allow you to avoid expectancy in strategies. So in, for instance, a priming experiment, one of the things that you're doing is you're having a relatively small number of trials that are related to one another. And those related examples, those are primes. If you see enough of them, then you start to expect them, and it changes the way you actually respond to the priming experiment. So they need to be fairly rare, and an event-related design allows you to do that, whereas a block design does not. There's no way you can do anything along those lines because by definition you need to have blocks of the same kind of trials. It also allows you to do sort of a post hoc sorting of events. So that is to say, you can look at the behavior of your participants and separate them out into correct and incorrect trials. So for instance, you could just sort of get rid of all the errors in your analysis and only do the analysis with the information that came from correct trials. And the reason I say that is that's of course exactly what we do with things like reaction times trials. We normally throw out all the incorrect answers and only analyze reaction times to correct trials because we know there are big cognitive differences. We can do the same thing with FMR if you can separate out the events and do it in event-related design. And then finally, if you are interested in estimating the shape of the hemodynamic response function, you need to use an event-related design because by definition you need these kind of transient events evoking individual examples of the hemodynamic response so that you can average over those and get a good estimate. The big problem with event-related design is the efficiency, right? It is a lot less efficient. You get smaller signals. So this is just a plot from a review paper where they were looking at neural adaptation effects. So before I talked about this in week 1, where you get this reduction in bold signal when there are repeated events. Well, that reduction is of course less than the whole bold signal, so already it's smaller than the basic signal that we're interested in. But you want as large a reduction as possible. And for instance, in a block design, you can see that it's a really nice, robust difference between lots of novel events and lots of repeated events. And this difference here is what we'd be detecting. Well, this is the same stimuli done in an event-related design where there's still a difference and you can see it, but it's much smaller than the difference that you would see in a block design. So you greatly reduce statistical sensitivity whenever you use an event-related design. There are also other issues, things like task switching. So if you have people responding to all the red words on the screen differently than all the blue words on the screen, then if they're happening in events that are just happening in random order and with a sort of a jittered temporal sequence, then they're constantly switching tasks. They're like, okay, that's a red word, I need to do this. That's a blue word, I need to do this. And that's different from perhaps the way they respond to the words themselves. So those task switching costs are enhanced in event-related designs. In addition, there's a very strong effect of presentation rate. And I've shown you slides of this. So if you're on average using a faster presentation rate in a purely event-related design, and you include temporal jitter, that improves your sensitivity. On the other hand, if they're fixed temporal windows, then it doesn't really make any difference whatsoever. You've got it basically as bad as you possibly can. And then finally, the analysis itself is a little bit more complicated and it's much more sensitive to the specific kind of hemodynamic response choice that you make. So often we tend to use an unbiased kind of canonical hemodynamic response because it's unbiased. It's just a sort of an average across people, across brain regions. However, you can do better. You can use much more sophisticated hemodynamic response functions and improve sensitivity in doing that, but only if you've got a good estimate. If you've got a bad estimate of the hemodynamic response, it's actually going to make your analysis less sensitive. So what's important here is that the event-related design is more sensitive to this specific choice. And what we normally deal with that is by using an average response. But if you're going to do something fancier, you need to be aware that there are potential gains, but there are potential losses in doing that as well. Okay. So to just review what we've heard in the first 2 videos so far, there are two basic designs. There are block designs, there are event-related designs. But of course, it's possible to combine these and get some of the best of both worlds. These are what's typically known as mixed designs, or mixed block and event-related. And often they take the form of this experiment that Eileen Cardillo did a few years ago, where she had people listening to blocks of sentences. So people would hear a sentence, and then they'd hear another sentence, and there'd be 45 seconds of sentences, followed by 45 seconds of sentences that had been digitally reversed. So you just take an actual sentence file and play it backwards, and it just comes out like an angry Eastern European speaking. So it sounds like a person speaking, but it doesn't sound intelligible at all. And of course, if you happen to be an Eastern European, it doesn't sound like an Eastern European language. It's just what a British person might think it sounds like. Okay, so she has these blocks of forward sentences and digitally reversed sentences that are each about 45 seconds long. So she's within that optimal time window. But within those blocks of forward sentences, she has 3 different types of sentences. So she has sentences that are where they end in a sort of a plausible way. The boy bounced the ball. But she has sentences that end in an implausible or incongruent fashion too. I like coffee with milk and hemlock. Now, hemlock comes as a bit of a surprise at the end of that sentence. And if you're familiar with some of the ERP literature, this is the kind of paradigm that elicits a very strong N400 effect because the final word is very much a violation of what you expected. This was an experiment that Cardillo did to look at where in the brain is possibly generating some of these N400 effects and what's happening with it. So by having these individual events, there are different types of sentences that are randomly interspersed and have temporal jitter between them, she's able to combine the best of blocks and the best of event-related design to try to tease these things apart. So for instance, what she finds is that if you look at where in the brain you get a strong response to intelligible speech versus unintelligible speech, you only are talking about a small set of areas to begin with. So then she can look within that and say, okay, well, where is there then a difference in areas that are sensitive to speech that are meaningful versus meaningless, right? And this is what you see here. You get this strong response in an area called pars opercularis in Broca's area, where you got the strongest response to incongruent sentences, I like coffee with milk and hemlock, and then a weaker response to sentences that make sense or even more neutral sentences. And again, if you just look at the y-axis here, you're looking at less than a 1% bold signal change that's being detected. So you can combine event-related and block designs to try to take advantage of the best of both worlds. So in this case, she's taken advantage of the block design to reduce task switching. So you're not just hearing random things and trying to figure out what's going on. They're all going to be sensible or they're all not going to be sensible. But within the sensible block, there are different types of sentences that you're hopefully not, expecting one form or another at that point, and therefore you can start to tease apart how your brain is responding to expected or unexpected endings. All right, I'm going to leave it there. The next 2 lectures in this series are both around design considerations, and they are the things you can look forward to next.